Hello community, so great that you are back. Let's talk about the latest AI research in swarm intelligence or self-optimizing multi-agent configuration. And you say, why need it? Now, easy. You have a complex open-ended problem like planning here multi-counter trade with dozens tricky constraints. This is where you need it. So either you build your multi-agent system and you have to be quite a good architect of multi-agent system architectures, or, and now today with a new publication, we are introduced to a new system, and it is called SwarmAgentic, towards fully automated agentic system generation via the swarm intelligence. And this is from our colleagues, unbelievable, in Munich, here in Germany. How beautiful is this? Now, if you compare this new SwarmAgentic method to all the other swarm intelligence solution, you see they have one characteristic features. They have a from-scratch agent generation multi-agent system, and they use here from theoretical physics here the particle swarm optimization methodology. Let me introduce you to this. This was published here on a conference in November 1995. Published in August 2002, my goodness. Conference was in Australia, in Perth, and this is, you see, theoretical physics, it carries over generations. But the idea is that you have a self-organizing mechanism, and this makes PSO particularly well suited for the optimization in complex search spaces. So you do have a position, you do have a velocity which updates its movement in the search space, and you have a simple mathematical formula here in theoretical physics here, where you see the velocity and the dependence on the velocity here in the time step t plus 1 on the velocity at the time step t plus additional factors. Beautiful. And you see, this is something what we observe in physics if we have the birds flocking or a fish schooling. This is nature, and those PSO models here adapt here dynamically to those processes. So incorporating shared knowledge from the complete swarm, balancing here the exploration of new possible ways and the exploitation of already known features. And I said, hey, yeah, let's calculate it. I connect here my best LLMs in the cloud. I start everything, I activate here all my numerical computer simulation programs, and nothing. Not only that they forget here to put up here, to fill up here the GitHub repo that they claim that they would publish, so not until now. I hope when you see this video, they will have all the data. But okay. But they promise us something beautiful, yeah? Democratizing complex AI. You no longer need to be an expert in agentic architecture. You just need this program. And, no human designer could ever map it out if we have real complex design spaces of agentic system so vast and so complex. No human can do this. This will lead to novel, hyper-efficient agent configuration. And you say, my goodness, their marketing is excellent. But if you forget about the marketing, you know what it is? It is a framework for AI that builds AI. This is it in case. So, where are the calculations of the theoretical mass? What are the calculations of the velocity of change or whatever we calculate? And the answer is nothing. Now, in a traditional PSO, you have multiple elements, but you have one that is a failure element. Then you have the personal best if you want, and then you have, if you want, a global best. And this is, of course, here in the configuration of the entire swarm topology. So, where is it now? How we do map this into an autoregressive AI system? No? Now, give you the solution. There are no direct numerical calculation in whatever way or form from physics or mathematics. No. The new framework is not manipulating floating point numbers in vector or tensor spacing or anything else. It is not the case, and I know you're gonna cry. Believe me, I feel it too. Because we have here from beautiful PSO equation theoretical physics, but in SwarmAgentic, in this framework, this is not an equation to be solved arithmetically. It is a recipe for a structured LLM-driven sort process. When you say, okay, so we replace here the dynamics of particles and physics here in numerical space with the dynamics of ideas in a symbolic space. Okay. So I needed to map this out for me. Maybe it is helpful. This is my own test. I run some experiments on this, and this is what I found. So step 1, we have initial proposal. No? I say design a multi-agent team to solve this travel planning task. And the LLM, whatever you take, GPT-4 Omni, for example, says, I propose here we create a planner agent to create the itinerary and a booking agent to handle here the reservations. And the planner will hand its output to the booker. Great. Then we have kind of a performance review and a critique. No? Because we have now a model, a 2-agent model. We run this and we get a performance report back. Of course, LLM is a judge. The performance report tells us the success rate is 11% or whatever. It doesn't really matter. No? But the important part is now that the LLM analyzes exactly why did I fail. So the prompt is now, hey, the system had only an 11% success rate, but here I give you the execution trace. I give you the reasoning trace that the LLM showed me in trying to find solution. And I tell the LLM, analyze the root cause here of the failure of this other LLM. And the LLMs come back with its critique and says, hey, the critique is that the booking agent failed because it was not given the budget constraints, only the itinerary. So this is a flaw in the collaboration structure of your multiple agent system. No? And also the planner agent, just have to tell you, lacks a policy for handling conflict user preferences. No? And now the most important part. In my configuration here, call it brainstorming, call it whatever, officially it's called the velocity update. So the system considers how to fix now the identified problems by drawing inspiration from 3 different sources. And those 3 different sources are our mathematical elements in the PSO equation. So at first, as I told you, failure. The failure-aware element. Yeah? The LLM now thinks, not calculate. It just thinks, hey, my last attempt to fix this just by reordering the sequence of agent failed. So the real problem is here missing information. The LLM says, I argue we need to modify the information package passed between the agents. Now, the second term in the mathematical equation of PSO is personal best. And we take this same idea and the LLM says, now, I argue we should revisit here a previous design of mine. Because the agent is running in a loop and trying out something. And it says, hey, my best performing system had a specific, say, constrained checker agent with a specific role in this configuration. So let's introduce this concept again. Let's make it a 3-agent configuration. Let's run it, let's evaluate it and see if in the reasoning traces we achieve now an improvement of the system. But hey, we are operating in a swarm. So the third element in the mathematical equation of PSO is the global best. No? It is the intelligence of the swarm. And now you say, hey, the best system in the complete swarm as a multi-system had an equality assurance specialist agent that does a final review of the entire plan against all original constraint in the human prompt. And the LLM, knowing now that somewhere in the complete swarm there's one particle that has developed this specialist agent, and it says, wow, this has a great performance. I try to integrate this into my idea. Now, what we have to do, or what I had to do, is map now from theoretical physics the formula that I know into this new symbolic reasoning pattern space. So I go here from a vector space in mathematics into a very open symbolic reasoning pattern space where I want to find solution. But this mapping, I have to understand what goes with what. So let's have a look now at the element. What is originally the velocity here, VI, is now the plan for improvement. And this sounds crazy, but give me a minute. What is this? This is a structured textual set of instruction on how to modify the complete agentic multi-agent system. The second important part are the coordinate system, the position, in a 3-dimensional space or n-dimensional space. No? So the current system configuration, the state that the system is in. But we have here full textual, or if you want code, Python, JSON, whatever, description of the current multi-agent system. It's a snapshot of now. And if we have the position and the velocity, then we have to have this learning element. And you see in the time evolution now we have 2 further elements. And the first one here has, for example, a PI in it. What is it? This is the best configuration found by this particle so far. Particle is our multi-agent system. Sorry, I have to explain this a little bit later. So this is a saved copy of a previous run that scores here the highest performance. And then this is if you want the self-learning, but here we have G. G has no index, so this is a global parameter, interestingly. And yeah, it is the best configuration found by any particle that is an element of the complete swarm. So this is a copy of a system with the highest score in the entire swarm. This is the best system, the best solution. So you see, so I see now my mapping, my simple understanding how I come from theoretical physics to computer science. So let's see this now in the light of the theorem. The theorem tells us we have three terms. The first is learn from its own mistake. So this is the failure aware component. Sometimes this complete term is here just an FI, whatever you like. It analyzes here the previous plans and why it failed to fix the problem. And then given here the execution of the reasoning traces, it looks at the reasoning traces and says, I think here I made a mistake. So the LLM proposes a new direction, a new element to add. And of course, like in any mathematical equation, we have three parameters. So we have a coefficient W. It just controls here how much weight you want to give to this don't repeat the failure logic. Now the second part here is you see operation. This is an subtraction. This is a conceptual subtraction. And this is what we call here the personal best guidance component. What is it? It is nothing else, if we transform this in a symbolic reasoning pattern, that it's comparing here the current system to its best own version before, and it generates now a plan to reincorporate successful past ideas or successful past functionalities or topologies of a multi-agent system. So this is the self-reflection element, and you have a coefficient C1. You can control the strength of this. And then, since we are in the swarm, now the swarm intelligence comes, and we have somewhere in the swarm, given you have a mesh communication, we have an open agent-to-agent communication, we have the global best. And this is our guidance component here, where we say, hey, this is the gold standard. Yeah? Now what we do, we have a mathematical operation here of a conceptual subtraction. And how we do this, we are not operating here in a numerical space, a vector space, a Boolean space, or anything else. We have a symbolic reasoning pattern space of our LLM. So we say, hey, compare the current system to the swarm champion system and generate a plan in plain English to adopt the champion's winning strategy and incorporate the best winning strategies in my current configuration of a multi-agent system. So if you want, this is kind of a social influence or a learning from other factor. And of course, we have coefficients and you can weight this in different forms. Great. And then finally, the result. If we operate here, if we do all these three operations, we have then synthesize and integrate this. So the final LLM task is that it takes here the three separate plans generated from 1, 2, and 3 and merges them into one single coherent deduplicated final plan. And this final plan will be the new velocity. The technical terms are a little bit strange, especially if you are a trained theoretical physicist. You say, what is this? But never mind, let's just go with this, and I want to give you an example. This is the test that I run that helps me to understand this. An operational example. A 7-day trip to Paris, budget is $2,000. I have 2 agents, a planner, a flight booker. I have already run it, where I showed that the flight booker just books here business class, and I have no money left for my hotels. So the personal best PI is already calculated, and the global best in the swarm shows me, if I have a dedicated agent that does here the function of a budget controller, then the performance improves. So let's start. Step A, the first term in my PSO equation is failure. So I say, hey, my last plan was just to add a hotel booker. This failed due to a poor coordination, and the prompt to the LLM is, hey, the previous plan to add a hotel booker was insufficient. Now go and propose a more robust strategy to solve the budget coordination problem. and the LLM thinks about it based on its internal knowledge, based about its pre-training data to solve this particular task, thousands and thousands of examples in the training data set, and comes to an output, a plan here from the first term, and it says, hey, I develop a new strategy. The problem is not the number of agents, but the kind of interaction. So I suppose a sequential workflow is required here. The second term in my PSO equation is personal best. So we have a 2-agent system input and a prior experience of a 3-agent performance data. And the prompt is simple. Compare the current system with your personal best. Your personal best system, if you start, of course, the history is 0, but you have to run it in a loop. Your personal best system correctly identified the need for a hotel booker, but failed on coordination. Now propose a refinement. And now the LLM, let's say it's a GPT-4 Omni or whatever you have, has to be trained on this kind of problem. What to do if I encounter this situation? What are the possible solutions to find high-performance solution patterns? And if it was trained on this in the domain, it will come with an output that says, hey, I propose the following, reintroduce the hotel booker agent again, modify the workflow so the planner hands off to the flight booker, which then hands off the remaining budget to the hotel booker. Step C is now, since we are in a swarm, we look for the global leader. And I say, analyze the global best system in the swarm, which successfully manages its budget best. Maybe it contains, since we have a mesh communication from agent to agent here, a budget controller agent. How can this concept be adapted to improve our current system? So you see, I don't hard code now, just copy this, but you say analyze this system, find the critical success component for this, compare it to our current system, and imagine, and this is really imagine, how we can improve our system given that we know that on a complete different system, some complete different solution worked. If you do this with a small language model, you will fail. 8B, 13B, no chance at all. You have to go to the big guns. You have to go 671 billion free trainable parameter models. The output here from the global best is now the plan. Introduce a new budget controller agent. You have seen somewhere this works. So all the booking agent must query this controller for approval before making a transaction. How beautiful is this? And then the synthesis. All the reasoning comes together. You have 3 plans generated above, A, B, C. And now A, B, C, what you do, you synthesize this. No, the LLM has the task. Given its understanding of the task, given its understanding of the environment, given its understanding of the complexity, now the LLM should synthesize those into the single best and most coherent plan of action that will provide the best solution. If the LLM was not trained on this task, the LLM will fail miserably. So you see the degrees of freedom we have and the pre-training necessary for those. It's all about reasoning. You need LLMs that excel in causal reasoning, in logic, because it has to analyze all those sequences. You can write this here in JSON. You can write it here in a Python dictionary. I don't care. What we have, ABC, add agent budget controller with a particular policy, add agent hotel booker with a particular policy, modify an agent, the flight booker, with a new policy, an updated policy, reconfigure them, not forgetting here the complete workflow because we modified some of the elements here of our multi-configuration system, and that's it. The LLM should do this alone, somewhere in the dark, without a human guidance. You see what we have. Coming back to the technical terms, this final structured plan, this here, is the velocity. Sounds crazy, is crazy, never mind. We just transfer mathematical formula into an idea space of linguistic. Okay, let's do this. And then we go in the loop. We go to the next time element. No? We say the next step is for another LLM to take this plan, the current system, and actually perform here the code or the system configuration rewrite. Test it, get the performance, analyze the reasoning traces, see or assume where the error happened, and try to optimize here the control flow. Now, I personally found that there's a kind of sensitivity to the initial system conditions. No? But at first, I mean, it still makes me crazy. You know, a particle from physics is now reinterpreted as a complete end-to-end multi-agent system that has its own configuration dynamics over time. This is not a particle, but okay. Okay, I'm generous today. So we have to start somewhere. And I need an example. So I say, okay, at the beginning, t equals 0. And I go with here n equals 5, so I go with 5 systems. The LLM generates initial starting systems for my travel planning task. And my 5 LLMs can have different temperatures, low, medium, high, and different configurations, different hyperparameters. So my multi-agent system 1, that is now called particle 1, okay, is simply a system with 2 agents, a planner and a booker. Particle 2, 3 agents, A, B, C. Particle 3, another 2 different agents. Particle 5 is interesting, a single monolithic, especially trained agent only for travel. This is now interesting. How does a monolithic single agent performance compares to an optimization of a multi-agent system that is operated within a swarm where we have multiple other examples that evolve in the same time constant? Talking about evolution. Now let's start it. Press the start button, off we go. Those 5 particles now, particle multi-agent system, you know, evolve now in parallel. And now, let's say we are at particle 2, we have 3 agents, and we evaluated whatever was the idea. And it gets a good score, né? So it self-reflects at its own performance, it compares its performance to the current best leader in the swarm, and then the LLM-driven velocity calculation might produce now a plan looking here at the champion in the swarm and says, refine the budget analyst policy and add a verification step inspired by a particle, our champion, booker agent. So agent-to-agent mesh communication, everybody talks to everybody. And we see, well, particle 2 sees that the performance of particle 1 is much better. It analyzes why. It detects in the topology of the multi-agent configuration there's a particular agent called booker. It analyzes the performance within the multi-agent systems, and the LLMs, being a super intelligent being, comes back and says, I want to integrate this in my configuration, but my configuration is completely different. So the plan is then to modify now particle 2, so its internal multi-agent configuration is now rewritten by its own LLM. But it might decide to go now from a 1, 2, 3 system configuration to a 4 agent structure with the booker agent integrated, because now it has also to rewrite here the flow, and it has to rewrite other dependencies. So this might backfire significantly. So you have to have a trained LLM for multi-agent optimizations. So you have to build here the training data set. Now, you know, the scoring agent is one of the most important because we have a velocity LLM, so used to analyze the particle situation and generate a plan, a strategy, the forward strategy to change it. The position LLM is used to execute that particular plan, that strategy, that velocity, and rewrites the particle internal code representation. But we have to have an evaluation, yeah? Because we have to judge the output of a particle if this is the direction we want to go to, or we say no thanks. So at every time step, all the multi-agent particle systems, they evaluate their own internal system configuration performance, and they communicate their scores, their benchmarks, to all the other members in the swarm. So what happens at each iteration t? So every particle I, which is a completed multi-agent system, runs its task, and it gets evaluated the result by an external judge. Guess what? The external judge here, the J here, is another LLM. Then the score is recorded, put on a leaderboard in the mesh structure so everybody can see it. And one is the winner. So we just list here, and the one with the highest score is seen all across the swarm. Any particle has access to this performance data. And now every particle knows its own performance, the best myself, my self-reflection, and it knows who the current champion is, what is the champion configuration, what are the features of the champion, and what is the communication pattern. Is it linear, sequence, parallel? it can analyze this and adapt this structure as it analyzed here the critical component in a 12-agent configuration and brings it back home to its 3-agent configuration, and it has to modify. If you have the feeling that at this time the LLM must be amazingly intelligent, absolutely. So while each particle, and this is a multi-agent system, is evolving on its own, it is constantly looking over the shoulders of the others, and it looks over to the champion, and they learn from each other. Né? And we have a score, it's transparent, beautiful. But don't make the mistake that you have the wrong implementation. Né? Because if you just look here, let's say you are a 3-agent system, and you see the global best in the swarm is a 7-agent system. And there is one validator agent with a specific role for the 7-agent system. Do not go and copy just the agent called validator and copy the functions of the validator in relation to the other agents, because this will fail. You are not a 7-agent system, you are a 3-agent system. So, copy-paste, no way. The LLM has to analyze this strategically and then implement this in a 3-agent system configuration. And if it's not in the pre-training data, my goodness. So you don't pick here the single best performing final system at the end. The swarm has this beautiful feature. During the flight, during every second, you share information across the entire swarm, across the entire mesh communication network. And whenever one particle has a breakthrough, develops something, or sees the sunlight or whatever, has or acts in a particular way, becomes the global best for a few iterations, all the rest of the swarm adopts. Now there's the problem, maybe the attention span of single elements in a swarm is not on a complete swarm, but only on a closer local environment. But let's make here a mathematical simplification. This mesh is lightning speed, complete, penetrates the complete swarm communication protocols. And then you can see exactly, you see the shared ideas and you can optimize yourself. So you have kind of a cross-pollination all over the place and ideas spread like wildfire. You do not have isolated silos, but you have an interconnected experiments. And I think this is the beauty of swarm intelligence, and this is why I'm looking forward to more of swarm intelligence. Now, unfortunately here, as we see by Anthropic, published June 13, the hub and spoke system that they have a central, if you want, orchestration agent. This is not the way forward. This is not an effective approach to multi-agent system. Yes, you can have this as the very first step if you try it out. But just think about human teamwork. It doesn't really work if you have one boss and the boss delegates you the work what every person has to do. If it's not a team, you just lose performance. And the same is happening in multi-agent systems. What I still struggle is still this mapping of a mathematical, theoretical, physical formula into the abstract symbolic argument space. And then I just have plain English language. So I don't need to code anymore. I just talk to my LLM and this is it. And the PSO formula is not translated in some intermediate formal logic for some solver or a new programming language for multiple solver tools. Nothing. Okay. But just remember, no? All this operation that we see in the PSO formula is not done now on mathematical levels. No? It is simply done on a prompt level. So this operation is now, in plain English, compare this system to the champion system, G, and tell me the key differences and how to adopt the good ideas. Now you see this has so many degrees of freedom. This is not a system you would use in theoretical physics. This you could just kind of operate here in computer science. Science, computer code. And also other operation. You just say, hey, please take these 3 different improvement suggestions and synthesize them into one single coherent plan. The option how this LLM is performing this are 100 or 1,000 possibilities given the complexity level. So you need the right LLM for the right job, for the right complexity. Otherwise, you lose performance like crazy. complexity, reasoning ability, creativity, directly determine the quality and the sophistication of the solutions of the framework that the LLM can discover. More advanced LLM, better. Different ways, better improvement strategy, multiple ways. And if you think you just need a big LLM and it will work, look at those videos and you immediately understand. No way. I want to give you 3 examples. Let's say we have a diagnosis for some flaw identification. And a less capable LLM, the old GPT 0.3, says, I can only have a surface level analysis. And I just noticed, hey, the output was incorrect because the budget was exceeded. That's all I know. I don't have more intelligence. This is it. Now, a more advanced system like GPT-4, for example, or 5 if you see this video, can perform now much deeper root cause analysis. And it might say, hey, the budget was exceeded because the hotel poker agent and the activity poker agent operated independently without a shared real-time budget tracker, and you got the idea. Let's have a look at this velocity generation if we have more creative and strategic solution to the planning phase. The LLM's capability to understand the environment, understand the complexity, come up with complex solutions to complex queries is paramount. A less capable LLM might suggest simple local fixes. An example I found, modify the prompt for the hotel booker to remember the budget. But this is a one-time, one-step patch. It's not a solution for the process optimization. However, the new advanced LLM can say, hey, I can invent novel strategic solution like a new agent, a new role. I propose that we introduce a new agent called the budget controller. All booking agent must request now from this controller. Or I have new collaboration patterns. I restructure the workflow from parallel to sequential for particular time periods for critical whatever. Or I make policy changes on a more complex level. How beautiful is this? How more chaotic is this? How more hallucination prone is this? Well, what about synthesis now of competing goals? You saw this in ABC, no? So the velocity update now requires here balancing 3 inputs. The first term of my PSO equation, failure, personal best and global best. And a less capable LLM said, hey, just staple the ideas together, ABC. If I try to find a summarization, maybe I create a contradictory plan. I don't want to do this. I don't have the intelligence. No way. I don't even know how to do this. I was not trained on this. Great. So you need a huge LLM. You need a cloud LLM. Don't go for quantized version or whatever. Do your own test, by the way, for your domain. In mind science, it's not working. So advanced LLM, more nuanced synthesis. Might reason, hey, the global best suggests a complex 7-agent solution, but my personal best shows me I'm simply a 4-agent system, and this is more robust, so I will adapt only the single most important agent role from the global best, the 7-agent solution, analyze it, extract it, optimize it, and integrate it then into my simpler proven architecture, reconfigure here the complete workflow algorithm, and find a new solution. Congratulations to your LLM, it is excellent. And you see, a lot of people ask me, why you focus on reasoning? Advanced reasoning is the most important factor for the next generation AI. It is the most important factor for a vision language model because all the reasoning is happening in the language model. And if you have a robotic vision language action model, the most important factor is the reasoning that is happening in the language model of the robotic system. Performance data. We need performance data. On creative writing is now the task, not travel, okay? So when transferring the best agentic system discovered by GPT-4o Mini, a real tiny one, to other LLMs, let's have a look at the performance. And you see all the other methods, beautiful, that came before. And now here, the SwarmAgentic. And independent, if you go with GPT-4 Omni, Claude, DeepSeek version 3, it outperforms the other models. Congratulations. But there was almost one point that I was missing because there is a Gemini 1.5 star. And I almost overlooked this. I said, what is this star? And here the authors made something genius. They said, you know what? Don't go with a GPT-4 Omni. Let's train this, the agent here, on a Gemini 1.5 and test it on a Gemini 1.5 Pro So go with the next level GPT, next level AI system, LLM, and let's see if we can improve from a GPT-4o mini 7.5. Yes, you can further improve. So it depends on the quality of your LLM that you use for this, and if you transfer it to others. So the better the model, the better the result. Interesting. And then they said, we found here there's a dependence. If you have here, and let's say we have here an agent that is called the quality assurance specialist agent. Great. And you see the success rate here only from 5 to 30%, so really low. If we introduce here a verification step, you see, wow, we make a jump. And if we have the verification step to confirm we need to the budget needs, another jump. And if we say we update now the quality assurance specialist to ensure the budget compliance for particular reasons, so the agent becomes better and better and better, you see, yes. But you know what? We not only improve the single agent performance, but we add LLM on top of LLM for simple substacks here, as you see, for quality assurance specialist agent. Why the hell can this not be done by a monster AI system that can do this internally? The answer to this question you find in this video. It will be interesting. But of course we talked about scoring. We talked about grounding this in real performance. Again, we need the objective function. If you want to read a little bit more about the development in AI, about the next step in objective function, this is the video for you. I'll show you a new code if we go beyond classical AI system. But let's stay here and we have the ground truth anchor. This is our objective function. Eh? We need to evaluate all those solutions. No? So we have here a process that has a high semantic diversity, because if I tell you you need a controller agent, I as a human, I think about other controllers because I know the human controllers in the real company, and I know their function, and I know their interaction with the other processes in the dynamic evolution here of the company performance. But if I talk to a Llama 4 model that doesn't exist anymore, and I talk about controller, maybe the Llama 4 will have complete other ideas. And maybe a Gemini 2.5 Pro might have a much different training data set it was trained on. And maybe we have specialized AI system that were trained only on business logic, financial optimization. They will go for something completely different. So you see, we have a linguistic semantic diversity in the technical terms because we are not operating here in mathematics. We are operating here in language. And language is so much dependent on your environment, what you know, and how you interpret semantic terms. So this leads us to a vast spectrum of possible agentic systems, agentic system operations, and performance data. Think about a genetic pool. And you have this permutation in the genetic precision over hundreds and thousands of generations. This is kind of a similar kind of evolution given the semantic diversity in this pattern space. Now, it sounds absolutely uncontrolled. No, this is open to interpretation. No, we have an objective function. We evaluate the result. So, we have different tasks, but let's go with a travel planner. That's easy. With a judge is a deterministic rule-based Python script, and it simply checks against the list of my rules. And if I define my query, I say, hey, on Monday I want to start in San Francisco. On Tuesday I want to be in New York for a step over. I want to be there for, 18 hours. I'll have a budget for a hotel of $20. And then I want to go 3 days to, Madrid. And then I want to go 4 days and visit my aunt in Rome. And then I want to take the boat to go back to, Rules. Simple rules. Budget, check. Monday in San Francisco, check. Tuesday in New York, check. Simple. You have scores. You can go with a scale 1 to 5. You can aggregate the scores. Beautiful. Or other constraint. Super. For some creative writing task, it becomes much more wobbling. So what you need a better AI system like GPT-4. This acts like a proxy for a human critique. No? This will understand if I'm here very emotional maybe, or creative writing or whatever. But it's also depending here on the pre-training data. No? And then for me, it's easy. I say to the LLM, hey, please rate this story's coherence, the story creativity, and adherence to the source themes on a scale of 1 to 10. So this is easy, no? But this is highly subjective here to the quality and the experience and the training and the domain specificity of the LLM. If it's all language-based, language is not like a theoretical physics mathematical construct. Language opens up itself to amount of possibilities. Here you see the conclusion by the authors. I always give at the end of the video here, short time here. This is the official conclusion, a screenshot. And they say, yep, SwarmAgentic, the model bridges here the swarm intelligence and the autonomous agent evolution, paving the way for scalable, self-optimizing agentic systems. Real nice. If you want to see my other video on swarm intelligence, almost a year old, more from a theoretical physics point of view, this is the video for you. Now I thought at the end, if you are interested, why not a challenge? Let's test out my knowledge and your knowledge here after reading this. So I think the abstraction of velocity is more or less of the original planning process of a multi-agent system orchestrator. And if we go to the simplest system configuration like Anthropic is doing this, no, the central orchestrator defines here an iteratively optimizing planning process for the multi-agent system, integrating here simply the data feedback. But now in the swarm, we have a complete different story, no? Because, and this is more or less the question, is the SwarmAgentic planning template, this means the strategy, based in the swarm and therefore integrating the term of failure, the personal system best, and the best here in the swarm representation? Is this not just another abstract symbolic programming, kind of parallel to the particle swarm formula, equal to a coded instruction template? If you want to learn more about this or continuous thinking, and in the last video I showed you, here Stanford showed us that we can outsource this thinking process from our LLMs, and we can bring the big LLM thinking process that took 10, 20 days or hours on high cloud compute infrastructure. We just can copy the planning in a test time cache optimization and bring it home to our local LLMs on our local laptops and optimize here a multitask performance here for smaller local LLMs. So this outsourcing of thinking, especially in the planning process, kind of coincides, what a surprise it is also in my videos, the very next video, with the planning template. This means with the strategy document for one multi-agent subsystem in a swarm of multi-agent subsystem. So think about this. It's not a coincidence here. And I can say, hey, if we established an entire population of individual, and I say, no, wait, not individuals, but of individual multi-agent orchestrators, should learn not only from themselves, but from each other and from the collective intelligence of a swarm. If we increase now the complexity in the parallel learning evolution here, like a genetic pool learning, then I personally think AI will become interesting again, and we can discover completely new system. So if you're interested in this kind of videos, hey, why not subscribe, and I see you in my next video.